An electron moves in a circular path perpendicular to a constant magnetic field of magnitude 1.5 milliteslas. The angular momentum of the electron about the center of the circle is 2.5 times 10 to the minus 25 joule seconds. And we're supposed to find the radius of the circular path. All right, so when it comes to a cyclotron, let me just sketch what it's going to be doing here. We're going to have a negative particle that's moving in a circle. Now it's moving in a circle because there's a magnetic field present. And let's say that the direction is into the page. All right, we'll just sketch the path here real quick. And we want to use the right-hand rule or left-hand rule to determine what the direction of revolution is here. Okay, it's an electron, so I would use left-hand rule personally. So I just want to point my middle finger of the left hand into the page. Okay, so let me try to draw the left hand here. All right, so the middle finger, when it's pointing into the page, I'm just going to represent that with an X. Okay, this is the pointer. And then here's the thumb, actually. And then the middle finger, you just can't even see it because it's pointing directly into the page. All right, so I've got the pointer going in the direction of velocity. The thumb is pointing in the direction of what would be called the centripetal force, but it is also the magnetic force, see? It points in towards center. So that left-hand rule just lets me figure out that this particle must be revolving in a clockwise fashion. Okay, so that means its velocity is going to be to the right here, it's down here, it's to the left here, because we always want the velocity to be just tangent to the circle. And there we go, we get nice centripetal motion for that particle. And this is the magnetic force. All right, now they give an angular momentum. So from physics 1, there's a formula for that. L equals R cross with P. L equals R cross P, where L is the angular momentum. R is going to be the radius, and P would be the linear momentum. All right, so R and P are always going to be at 90 degrees with each other here. So if we just try to find the magnitude, if we find the magnitude of the angular momentum, that's actually what we were given right here. So to do that, we would use L equals R times P times the sine of the angle between them. But the angle between them is always going to be 90. So let's just write L equals R times P. Okay, and then P has a formula as well. It's mass times velocity. So we can go even farther and do L equals R times M times V. Alright, so what I would do next is plug in the angular momentum that we were given. I'll leave R as just unknown. I can use the mass of the electron. And then we have the velocity. Unfortunately, though, we don't know the velocity. All right, so what other formulas do we have that can help us solve this? Well, we know that we need the centripetal force to equal the magnetic force. Okay. And we have a formula for each of these just from the past. From Physics 1, centripetal force is mv squared over r. And we have a formula for magnetic force, Q times V times B, as long as they're, it's a cyclotron. I'm going to put an absolute value around the Q, though, because I want it to be positive. The centripetal force is, it's going to come out positive because your radius is positive. Your velocity gets squared. So just to be mathematically precise, I'll put an absolute value around that. All right, then if we rearrange, we can actually solve for r by moving the r over to the other side and then taking all this stuff and moving it by dividing to the other side as well. We get a new formula when we do that. R equals mv squared over qvb. And then we can cancel one of the v's, revealing this nice, concise formula for a cyclotron. Now that would especially be useful in this problem because, as you can see, we have the r, and we'd really like to just replace it with other quantities that we know. So it looks like we'll be able to do that. I'll take out the r, and we'll put mv over qb in its place. All right, with this in mind, we should be able to solve for v first, which would be the speed of the electron. Then we can go back and get the radius as well. All right, so let's plug in everything that's missing here. All right, I'm getting 8,500,000 meters per second. So now we can go back and find that radius. I'll just use the formula here in the upper right. So we want R equals mv over qb. So 9.11 8,500,000. Charge of electron. B field. Alright, I'm getting a radius of about 3 centimeters. 3.2 centimeters.